Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today I want to discuss about the selective topics related to this engineering tribology. So already we have studied about friction, surface interaction, and then wear and lubrication and corrosion and other material properties also we have seen. So in this session, so I want to discuss about some topics related to this surface interaction and friction. So the surface treatment and wear. This is already in 2 and 1 we have discussed about friction and surface interaction. Now in this you will see the wear and surface treatment. So what is very important thing in the engineering tribology subject. It plays a main role. So wear refers to the gradual removal or deformation of material at solid surfaces due to mechanical action, such as friction, cutting, or sliding. It is a common phenomenon in mechanical systems and structures, so impacting the performance and the lifespan of components. Wear can occur in various forms. So depending on the conditions and materials involved, some primary types of wear given, the abrasive wear. The description is this type wear occurs when hard particles or hard protuberances force against and move along a solid surface, so leading to material removal. So this is comes under this abrasive wear. So generally, the wear refers to the gradual removal or deformation of material at solid surfaces. So the abrasive wear, this type occurs when hard particles or hard force against under this move along a solid surface. The types are two body abrasion, that is abrasive particles are fixed, and three body abrasions, the abrasive particles are loose. Examples: sandpapering, erosion of pump components by sand particles in water. Next, adhesive wear. Abrasive wear is over, and then adhesive wear is caused by the formation and breaking of adhesive junctions, cold wells, between two sliding surfaces. Mechanism is when two surfaces slide over each other, the material transfers from one surface to another due to adhesion property. So examples: galling, scupping, and printing. So these are the examples for this adhesive wear. So generally this type of wear occur due to the breaking of adhesive junctions between the two sliding surfaces, the corrosive wear. So wear accelerated by the chemical or electrochemical reaction with the environment leading to material removal. So the mechanism, oxidation or other chemical reactions weaken the material, which is then removed by mechanical action. The rust formation on steel surface, degradation of metal surfaces in acidic environments. Next, fatigue wear. So this type of wear occurred in whenever the component is subjected to repeated loading, so that the repeated loading, the causes caused by repeated loading and unloading cycles leading to the formation of cracks and subsequent material removal. The mechanism surface fatigue due to cyclic stresses results in fitting, swelling, and or cracking. So examples: rolling contact fatigue in bearings, gate tooth fatigue. So erosive wear. So erosive wear is the main definite description is caused by the impact of solid or liquid particles against a surface. So the mechanism is particles hit the surface with high velocity. So due to this particles velocity, the material, the particles may be solid or liquid, that impact against a surface. Due to this impact force, some material will be erosion. So that is removed by cutting or deformation. So erosion of turbine blades, wear in pipelines transporting slurry. These are the examples. Fretting wear. So the main description is occurs due to small amplitude oscillatory motion between two contact surfaces. The mechanism, the repetitive motion causes surface degradation and the formation of wear particles. So fretting in bolted joints, contact surfaces in electrical connectors. So the cavitation wear. So the caused by the formation and collapses of vapor bubbles in a liquid near a solid surface. So the mechanism is the implosion of vapor bubbles generates shock waves that remove material from the surface. Due to the vapor bubbles generated and then shock waves that removes the material from the surface. So damage to ship propellers, pump impellers, and hydraulic turbines. Next, surface fatigue wear. Very important topic. The surface fatigue wear occurs due to a repeated cyclic stresses acting on the surface of a material, leading to the initiation and propagation of cracks. So over time, these cracks grow and intersect, causing material fragments to detach from the surface. So this type of wear is commonly seen in rolling contact situations, such as in bearings, gears, and cam polyer systems. Though the occurs due to the repeated cyclic stresses so acting on the surface of a material. So that is nothing but the surface fatigue wear. So examples such as in bearings and gears and cam polyer system, this type of surface fatigue wear you can see. The mechanism. So what is the mechanism behind this surface fatigue wear? Micro cracks form on the surface due to cyclic loading initiation. Propagation, these cracks grow with continued stress cycles. The material removal, eventually the cracks intersect and lead to the detachment of material particles, resulting in a fitting and a swelling or flaking of the surface. Examples, fitting on gate teeth, spalling in ball and roller bearings, crackling in railroad tracks. Next, control of surface fatigue wear. So one is material selection, is very important, and surface engineering. So material selection, use materials with high fatigue strength, toughness, and hardness. They employ surface treatments like carburizing, nitriding, or induction hardening to increase surface hardness and resistance to crack initiation. So that's why the selection of material is very important in a design. So if you have selected a good material for a good proper application, so you can control of the surface fatigue wear. You can minimize. So that's why you should know about this surface fatigue wear. The surface engineering apply coatings such as chrome, nickel, or tungsten carbide to improve surface hardness and reduce wear. So use short peening method or laser peening to introduce compressive residual stresses on the surface, which helps to resist crack initiation and propagation. Next, lubrication. Ensure proper lubrication to reduce friction and wear. Use lubricants with additives that form protective films, reducing direct metal to metal contact and distributing loads more evenly. So the design improvements optimize component design to distribute loads more evenly and avoid stress concentrations. So the stress concentration topic is very very important in mission design. For design improvements, for to control the failures, you should know the stress concentration. You have to avoid the stress concentration. So use how to avoid this stress concentration. Use larger radii at corners and fillets to reduce stress concentration. Suppose the component is having this type of cross section, uniform cross section, there is no problem. There is no stress concentration while carrying the load or while moving just distribution lines from one end to this end. Suppose the object is like this, so there is a problem. The stress concentration will be occurred at this area. You should avoid this type of edges. You should avoid with large radius fillets. So that is design improvements. Regular maintenance and inspection. Perform regular inspection to detect early signs of surface fatigue such as micro cracks or fatigue. So schedule maintenance and replace worn components before significant damage occurs. Next, control operating conditions. Avoid excessive loads and speeds that can increase stress on the surface. So implement proper alignment and balance in rotating machinery to reduce uneven loading. By addressing these factors, surface fatigue wear can be significantly reduced, leading to longer component life and more reliable mechanical systems. Next, fretting wear. So the fretting wear occurs due to small amplitude oscillatory motion between two contact surfaces. So this type of wear often arises in mechanical joints where there is a slight relative motion between surface under load. So mechanism is the small movements, the repetitive movements cause surface degradation. So this leads to formation of wear particles and potential oxidation. It is common in bolted joints, spline shafts, and electrical connectors. Prevention is use of lubricants to reduce friction. The application of surface coatings or treatments. The designing for better fit and reducing relative motion. The surface fatigue wear. The surface fatigue wear caused by repeated cyclic stresses on material surface. Already we have discussed in previous slides. So the mechanism micro cracks due to cyclic loading. Next, erosion wear, and percussion wear. So this is where due to repetitive impact or hammering actions on a material, so leading to deformation, material displacement, and eventual wear. So the repetitive impact or hammering actions are subjected to a material. There is a percussion wear occurs. So due to this wear, what will happen? It leads to deformation and material displacement. The mechanism repeated impact causes surface deformation. The material may crack and fall off due to the constant hammering. The common in tools like hammers and anvils, and in machinery subject to repetitive striking actions. Next, prevention: using tough impact resistance materials, applying surface hardening treatments, properly designing components to distribute impact forces evenly, regular maintenance to identify and mitigate early signs of wear. These brief notes highlights the key aspects of each type of wear and common strategies for their prevention and control. Next, Archer's theory of adhesive wear. This theory is a widely recognized model that describes adhesive wear, where wear occurs due to the formation and breaking of adhesive junctions between two sliding surfaces. Cold junctions, you can say cold junctions, the adhesive wear will be occur. So the basic principle is adhesive junctions when two surfaces come into contact, that is microscopic high points on each surface, interact and may form adhesive bonds. During relative motion, these adhesive bonds can shear, causing material transfer or wear particles to be generated. Next, wear volume. Archer's wear equation relates the volume of material worn away to the applied load, sliding distance, hardness of the softer material, and a dimensionless wear coefficient, that is K. So you can get where V is equal to KLD by H. Next, key components are wear coefficient. This is a dimensionless factor that accounts for the probability of junctions formation and the effectiveness of their shear. Typically determined empirically and can vary widely depending on material fairings and environmental conditions. The applied load is the normal load applied to the contact surface. Higher loads generally increase the adhesive wear rate. Sliding distance, the total relative motion between the surfaces. Greater sliding distances result in more wear. Hardness, the hardness of the softer material in the contact pair. So high hardness usually leads to lower wear rates. So it has a hardened material or more resistance to the deformation and adhesion. Next, assumptions. This theory assumptions, the model assumes that wear is proportional to the applied load and sliding distance. Proportional to the applied load and then sliding distance D. It also assumes that the wear debris is formed mainly due to the adhesive forces between the contact surface. So you can see here KLD by H. So K is here wear coefficient and L is here applied load and D sliding distance. So the wear coefficient assumptions the proportional to the applied load and sliding distance. The wear is. It also assumes that the wear debris is formed mainly due to the adhesive forces between the contact surface. Next applications are Archer's theory is used to predict wear in various mechanical systems such as bearings, gears, and sliding contacts. It helps in selecting materials and designing components to minimize wear and extend service life. You can improve the service life by using this Archer's theory. Various mechanical systems you can predict wear in bearings, sliding contact bearings, rolling contact bearings, and then gears. Okay, and then different types of gears are there, and worm gears and worm wheel. So all these components can be frequently subjected to wear. So you can predict the wear by using this theory, Archer's theory. So it helps in selecting materials and designing components to minimize wear and extend service life. Next, some limitations are there. So the theory simplifies real world conditions and does not account for all factors influencing wear such as lubrication, surface roughness, and temperature. So it simplifies the real world conditions but not accounts for factors like wear and lubrication and roughness. So it is primarily applicable to metal on metal contact, wherever the metal on metal contact, and may not accurately predict wear in non-metallic or composite materials. Example, gear wheels. And example, gears and bearings. In this, there is a metal on metal contact. So that's why this Archer's theory is useful, applicable to this type of applications only. So that is one limitation. So not suitable for non-metallic or composite materials. So suitable, you can use this theory, but you can't get accurate values. So accurately you can't predict the wear. So by using this Archer's theory, engineers can estimate wear rates. So before designing a component or product, various steps are there. First, you need to identify the problem and then select the material. And you should know the properties before selection of materials. So every engineer should know about the mechanical properties and thermal properties and electrical properties. So then only he can select proper material for proper application. So before selection of material, before designing, the selection of material is very, very important. So materials topic already we have seen, engineering materials, different types of materials and properties also we have seen. So by using this Archer's theory, so particularly related to this wear and surface treatment, engineers can estimate wear rate. So already we have discussed about this wear rate calculation. So how do you calculate the wear rate problem? So we have discussed in previous sessions. We did problems also and design systems to reduce adhesive wear. So improving the reliability and the life of mechanical components. You can increase the life of bearings. You can increase life of the gears by using this theory. So that's why this theory simplifies the real world conditions. So by using theory, the engineers can estimate the wear rates. So limitations over and assumptions we have taken. Uh, Main assumption is the wear is proportional to the applied load and sliding distance. The wear is applied load L and distance. You can see in this equation KLD by H. What is H? The hardness of the material. K is dimensionless wear coefficient. So KLD by H. So this is proportional to L into D. So you can write this equation with K, the coefficient KLD by H. So this theory helps in selecting materials and designing components to minimize the wear and extended service life. Clear? So here the wear volume Archer's theory main uh, aim is to minimize the wear, predict the wear. The theory of this adhesive wear, where the components are uh, breaking, the two surfaces are in between, adhesive junctions are occurred. So in between two sliding surfaces. So nothing but cold junctions. So limitations. So this one, this is related to this Archer's theory we have discussed, and problems also we have seen. So these are the references I have taken. So go through these references and refer any one textbook. You will get more information. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.